Final presentation of our structures class this semester, so thanks for teaching us for the last 5 weeks. So when we start off with this, we want to start off with like the very basics, like the kind of foundations for what kind of sets structural analysis. So kind of starting off with statics and the things we've learned some of those previous semesters. That like while we didn't necessarily apply them in this class, it kind of like the basis of the things we learned. So starting off with loads, we have like many. Like if you look at like a block on a slope, you have many different loads that are applied on it between like the normal force applied by the surface as well as the gravity and its two components, like parallel and perpendicular to that surface, as well as any friction that would be to be caused by that surface. And so there's the different loads that be applied, and then of course we can talk later about how, of course, the different loads that are applied will cause different moments, and how that can affect the structure. And so then when we extend this to the equilibrium equation for this, we have like the most basic equation from Newton's third law, where we say that the force is equal to the stress times the area. And so of course, as we increase the force from something like, the load or the weight of an object, but also if we make it bigger, you can decrease that stress by spreading out over a larger area versus if you have a smaller area that you're spreading that over. And then, of course, there's also the stresses on an object as well. So we have the normal and shear stress model. And so you can see like where we have both shear and tension and compression. So you can see we always define stresses based on their direction versus if we have like stress that are coming this direction, we consider that in tension just pulling out from that perspective versus in compression we have it pointing in. Versus then we have the diagram of all the shear stresses that come alongside the edges of what we just used as an example of a cube. And then for the constitutive law, we have the major kind of like the stereotypical, just the graph of the stress versus the strain. And so this, of course, vary by material, but this is kind of like the generic graph of stress versus strain, where you have the linear section, which allows you to define Young's modulus, like if you're do like an experimental test of a material that you don't know the Young's modulus, and then where you get the strain hardening and the necking, which doesn't always happens to different extents, different materials, or might not necessarily happen depending on what the material is. But you'll have after you have this linear section, you'll have a slight drop before the strain hardening occurs, and then the necking occurs, and then eventually the fracture. The ultimate strength is, of course, where you have the highest stress that occurs before you start to have that necking where it drops off and then eventually fractures. I can do this one. And then there's a different elastic moduli. These are kind of been big throughout the last 5 weeks. And so we also use these a lot later. So when we derive the C44 at the end, we use the shear modulus and the bulk modulus to help us define some of the previous equations that go into defining C44. So we have the Young's modulus, which is used like for the axial loading, and so you can see in this diagram here, just zoom it in a little bit more. A little blurry, but it's a little bit better. Or if we're applying a force kind of pulling out and tension on it, that's when we would define the Young's modulus, since it's in that axial loading direction. And you can see that like when you apply that type of load, you see this type of strain that's on the object. And of course, if you start to pull it out, you expect elongation, or if you're compression in, that sort of deformation. Versus when we have our shear modulus D, which is like if you apply a sort of shear load, you can kind of see what that shear strain looks like and how that's going to shear the object and cause that type of deformation. Versus in bulk modulus K for hydrostatic pressure, where like one of the examples we'll talk about later that Ivan will go on about, if you have like a submarine and you are acting like kind of an equal force or pressure that come in all directions pushing in, and you kind of have this shrinking of volume coming from the volume strain. Then the flexural modulus, which we never really talked about very much since we didn't talk so much about flexing of beams, but if you're looking kind of more towards civil engineering applications, that would be an important one. If you're talking about bridges or anything else that uses a beam, or if you have, of course, say like your supports here and you have a person or a car or some sort of load that's weighing down in the middle. That's going to cause a flexing of that beam that you want to minimize.
So even in aerospace engineering, the wings, for example, are
wings.
like beams which
Yeah.
are bending. Just that the boundary conditions are different.
So one of the equations that we didn't include yesterday was from the Kirchhoff-Love's hypothesis that you mentioned in your email. And so we wanted to really differentiate the units here, where previously we mentioned that it was mainly unitless, strain could be unitless. But if we do dimensional reduction, the units do change. And so in Kirchhoff's-Love's hypothesis, you'll notice that for 2D and in 1D, it can be both unitless and can have the units of 1 over m. Specifically for epsilon, it's going to be unitless, and for rho, it's going to be 1 over m. For the generic 3D kind of model, we can have the standard definition of what strain is, where it's the change in length over the original length, and that's one of the equations that we use throughout our rest of our presentation. And as Matt was talking about before, with the stress strain curve, there's the key point. One of the key points is the yield stress, where it really determines where the elastic and inelastic region starts. Where if it's elastic, we're able to reverse whatever change in loading happened, while if it was inelastic, the deformation becomes more permanent and hard to reverse and may lead to any structural failure.
Yeah, but the distinction between elastic and inelastic is more of a constitutive law, so it comes under an earlier column. But I see what you're saying in terms of the deformation. So it's good to classify that whenever you say just the adjective elastic, inelastic, it means it comes under the constitutive law, whereas when you're talking of elastic deformations and inelastic deformations, you might as well write out explicitly the deformation word.
Yeah, so later on we'll talk about specific examples of deformation with buckling and the bending moment. And also one more thing with units that I wanted to talk about was that the units for loading conditions aren't necessarily constant. Last time we had it as just purely newtons. We know that's not the case. With our example here, we know the point load or a concentrated load will have the units of newtons, where if it's distributed, it's going to be newtons over meters because it's distributed over the length of whatever beam is being applied on.
So that's a very important point because you're talking about everything in the generalized term. So, which is why they could have a wide range of units. It's just that you identify from the kind of variable it is whether it's one of those four, not from its units.
So on a bit on the side note, we have more circles equations that just go into stress. They relate normal stress and shear stress. It helps us to later go into constitutive law since we might want to look into shear stress from normal or vice versa. So for constitutive law, we have two matrices that relate all of the stresses to all of the strains. The first one was found from a deformable bodies class, which utilizes an assumption of in-plane stresses, which makes the so two of the shear stresses and one of the normal stresses equal to 0. This assumption cannot be used for composites since we want to look primarily at shear stresses and analyze them, and also from experience they're usually not 0, hence we need to include them, but in the end we have only 5 unknowns, so we can still analyze it well enough and computing powers are strong enough so that we can solve it in its current state. Also we have the Poisson's ratio, Poisson's ratio, can you do a bit there? Poisson's ratio, which basically relates the lateral strain and longitudinal strain, and which it also goes to the Poisson deformation in a way. That is that the cross-sectional area reduces if you pull out on the material, and it can increase if you compress the material as an extra shear as other shear normal strains based on one of the stresses, only one of the stresses.
So also what we have is this kinematic equation that basically relates strain to displacement as a form of deformation. In this case, we're specifically talking about rigid body structures. That's why you'll see that the derivative of u as the displacement field over dx will give us a strain in the x direction. And this is the same for the other examples of normal strain displacement, whereas you'll see in the shear direction, we're adding two different derivatives in order to finally figure out what the strain is. And next we'll talk about beam types.
I'm trying to. I'm just going to see from. So with different beam types, and we didn't go into this as much in this class since this would be more kind of a civil engineering application, but it's still kind of like at the core of structural analysis, and like still like generally like kind of what we elaborate on within beam types is kind of important also within aerospace applications. But with different beams, where they have like like the classic I-beam or the flange or the T-bar, they're going to have different moments of inertia so that we can find based on their shape. And so that's kind of the core thing that we wanted to elaborate on, where depending on what sort of shape you had, we'll go back up in a second. When you use the perpendicular axis theorem and the parallel axis theorem, where you can see like if we know, for example, up here, if we know what the moment of inertia of an object like about its center is, if we're going to want to find it about a different point, then we can use those equations. And so that kind of varies a lot based on if you're going to find it, for example, if you have a beam, but you're going to find about its middle versus find about its edge, basically where it's pinned, where it's supported. So for example, we talked about in class where you have wings that might be just a fixed like one point on the fuselage, versus you might also, we talked about the wings where we have the supports or struts that come up from the side, that those are going to have different types of supports. That of course affect how the moment acts on that wing. And so that's kind of even like a extension of, even though this isn't like specifically for a traditional beam, kind of extends this idea to like something that would be a concept within aerospace. And so as well for these constants, when we look at different types of cross sections, we have just like the standard definitions that you talk about within dynamics, other classes, where you can find the value of J just kind of based on its geometric shape. So whether or not you have like a square or rectangular cross section, or circular, or like a tube section or a hexagonal section, we're going to have different values of J, and of course that's going to affect based on what that cross section is, kind of what its way it's going to behave under loading or under moment. And so that can be an important thing to consider, like if we talk about the different cross sections of like what any sort of structure might look like, and like what makes sense from the point of view of if you're going to apply different moments or loads and where those have to come from. If you have a different value of J, or you move like where that load is acting on, that's of course going to affect how like that moment is applied, and how that might affect failure stresses on that beam or on that part of the structure. And we just also had like kind of like the generic equation for second moment of inertia here based on its integral. Like it just kind of briefly talked about for deriving where the perpendicular axis comes from these integrals to get this. And then of course just the generic parallel axis theorem, we can find the moment of inertia at any point based on the moment of inertia about its center, plus of course the distance from where that actually acts on.
Okay. So let's talk about aerodynamics. Very simply with loads, we can talk about lift and drag, thrust and weight, all in newtons, right? So we see that applied on an airfoil here with lift and drag directions based on the direction of the velocity of the fluid. And then here we have a basic diagram of a plane on the four major forces that are applied, if we were to zoom out, right? Now, let's take a look at, how are these forces created? If we take a look at lift here, we'll find that that's really related to Bernoulli's principle, which is as the velocity of a fluid increases, the pressure decreases, right? So we see as there's lower velocity at the bottom of the wing, there's higher pressure, and high velocity at the top of a wing, so there's low pressure, and that dynamic creates that lift that we were talking about here, right? And we can see that this lift can also be kind of reduced down to an equilibrium equation. So that's the connection here, is that the Bernoulli's equation is an equilibrium equation, right? That includes pressure and kinetic energy and potential energy, right? So here it shows that it's constant, right? And within Bernoulli's equation, there is pressure, right? And pressure can be basically interchangeable with stress, right? So this kind of derivation of the equation kind of keeps going. So we can see like weight over area, and then that eventually ends up with density, you know, and then, you know, units in pascals, right? So both pressure and stress have the units of pascals, right?
But those two are not connected. The pressure distribution on actual airfoil is much more complicated and intricate. That's something that is valid for a much simpler problem, but I see your point here.
So of course, another form of a load would be a moment, and we actually improved this picture from last time, where you'll see now the moment is at the tip of the bar instead of at the wall. So that's better. But we still included this diagram to the left or to the right, where we're basically trying to show this relationship between the applied load, the shear force that's created, and of course the bending moment, where they're all basically the integrals of each other. You can see that based off like the graph, we'll see that it continues down. And using these equations, we can actually derive both a stress from this, as well as later we'll see a deformation. And so the stress is, we have an example of this stress example where the moment in the z direction multiplied by the y divided by the second moment of area will give us a stress in the xx. So it's going to be a uniaxial stress here. And we can, while we have these equations, in order to fully solve them, to find displacement as an example of deformation, we need to know the boundary conditions on which the structure is existing. And so first we have the shear force and bending moment examples, where if it's free like you see on the right end, it'll have a shear force of 0 and a bending moment of 0, as well as if it was pinned, it would have a bending moment of 0. If we go to the right, we'll see more examples.
We can't generalize like that, because it also depends not only on the boundary condition but also the loading condition.
Yeah.
So for example, I can take a free beam like this. So let me take a free beam like this. So I can apply forces like this. So it's not actually supported by anything, but it will still have stresses.
Yeah.
Okay. So on the other hand, I could replace these two points where I'm applying the load with actually supports. So when I have supports like this, so then you could probably think of it like if it's hinged, a simply supported kind of a beam structure. So yeah, those are three different kinds of typical idealized boundary conditions. But V and M, to find that out and whether to say it's 0 or not, you need more information than that, the actual loading condition.
So then instead of just being 0, it can also be like a prescribed number that we know already, right? Is that what you're saying?
That's right, yeah.
Okay.
So typically, as we've been discussing, all of these are boundary conditions. It's a boundary value problem, right?
Yeah.
So, but boundary conditions themselves are of two types. One is the boundary condition involving with the geometry, which is what you're talking about from the free pinned fixed certain information that you can extract. But there are also boundary conditions associated with the load. So the particular area of the structure which is loaded in different manners. I could apply, let's say, a force with this, which means over that cross section it is kind of a distributed load that is there. On the other hand, I could apply it with a sharp pin. It's like a concentrated load that is applied there.
Yeah.
Or I could bend it this way, which is like a moment that you showed M0 over there. So all of those are also boundary conditions. They come under what are known as natural boundary conditions.
Okay.
So in your categories of equations, it's not only equilibrium equations, but equilibrium equations along with natural boundary conditions, which are essentially conditions about the load. Similarly, when you're talking about the kinematics, it's not only the strain displacement relationships. In dynamics, it will also be velocity displacement relationships, but also you'll have the geometric boundary conditions, like saying that if I'm fixing this particular end, then the displacement is 0, the rotation is 0.
Yeah.
Similarly, if I'm hinging it, I can only say that the displacement is 0,
Yeah.
right? So only the displacement is 0. But I can also see hinge is a very interesting case where you can have one natural boundary condition and one geometric boundary condition. Well, the natural boundary condition is that the moment is 0. The geometric, because it's free to rotate about the hinge, which is why it fell off. On the other hand, it's also mentioning that the displacement is 0 because it cannot move beyond that pin where it is pinned, right? So you could have some mixed kind of boundary condition, like pinned is a classic example of that.
Yeah.
Whereas a fixed end, both the conditions are geometric boundary conditions. It's saying displacement is 0, rotation is also 0, which is why when you draw the deformation of a cantilever, irrespective of how the load is, it will look very similar at the end which is fixed. It will always be 0 displacement, 0 slope.
Yeah.
So that's how it will be. On the other hand, if you go to free, it's the other extreme where you do not know anything either about because it's free, you do not know anything about either its displacement or its rotation. But you do know what is the load that you're applying, if you're applying. If you're not applying any load, you know that it is 0. If you're applying a load, you know what is the value of that load. It could be a force, it could be a moment, whatever. So that's the idea about it being free. So this, even though these are kind of idealized and can never be achieved in reality, they give you a lot of ideas in terms of how this distinction is there between what is typically in math called as Dirichlet and Neumann boundary conditions, named after the people who introduced these kinds of concepts. But more importantly and interestingly for us, one is about generalized forces, which includes moments. One is about generalized displacements, which include rotations.
So as you mentioned, we have more boundary conditions in the kinematics section where we're talking about just how you mentioned where for a fixed beam, the displacement will be 0 and the rotation will be 0.
Mm-hmm.
So that's just as you mentioned. And we also have the inclusion of pinned where the displacement will be 0. And furthermore, we have an image that shows basically how we got to this point where we know that the integral of going twice will give us both the bending moment. You'll see the picture of this bending beam where we have rho as the radius of curvature, which is the inverse of the Greek letter. And we have this here. And then in the full derivation, what we'll see is that we end up getting strain, where strain follows our original concept, where we said it was the change in length over length. And it ends up giving us negative y over rho. But since we know that 1 over rho is equal to our Greek letter here, and this is the second derivative, we can directly just say that solve for strain here. And furthermore, we have both the two equations that show that taking an integral of shear force will give us the moment, taking the integral of the loading condition will give us the shear force. And one more thing that I added was an example of buckling due to an axial force being applied. So if you have a rod that's already bent, applying an additional axial force along those two ends will cause additional deformation. You'll see the equation, while it is similar, has additional terms. And what's interesting to note here is that we have this new term where it's the elastic modulus times the moment of inertia or moment of area, I effect. And this is like an effective version because when you're putting a load under compression, the stiffness does decrease because of that. And so that will affect how the deformation acts. And in this, we can actually just figure out what the critical load is to where failure will occur. And we find this to be pi squared times elastic modulus times I over L squared. And also we included units of, for, in this case, since we were talking about displacement or deflection, the units for here will be meters.
Yeah, you mentioned that it's not only this load, but there's also some other load. It need not necessarily be.
Yeah.
Even with just this load, you typically will have, beyond a particular value of that load, it getting into a buckled shape. The reason it happens is, could be multiple reasons. One is if these are not directly aligned to each other, there's a slight misalignment because that could be a eccentricity allowed with the load. The other could be in terms of the geometry. There could be an eccentricity because of the geometry, the way the structure is made. The other could be because of the material distribution. So once again, you could have eccentricity because of that. the final thing could be, because this may not be just in vacuum, it could be in, exposed to the atmosphere. So it's just even a small wind, for example, or anything, small disturbance that is there, it's just a tap without even actually applying much of a force, just a tap that you give, that all of that can make it move in a particular direction. Otherwise, there's no special reason for this to move either upwards or downwards.
Yeah.
So why is it moving in a particular direction is essentially because of these eccentricities, which could be with the load, the material, the geometry, or any external disturbance.
So I guess in this case, we're talking about it. We're not including any eccentric loading because it's acting directly on the middle
Right.
eccentric.
Ideally speaking,
But if it
that's
was
how we
eccentric-
get for the model. But that's what happens in reality. The reason it bends. So you will not actually be applying any load in that particular direction. Just so happens because of the imperfections that are there in the actual system, which is not idealized. So this is another thing that in our modeling, when we make assumptions, we make a lot of these idealizations, right?
Yeah.
So like what we were listing out for all those 8 different or 10 different assumptions that we made. Some of them are acceptable. Most of them were related to materials, but there are also certain things associated with the loading condition, with the geometry, with the material distribution. We assume it's kind of uniformly distributed, etc. Many a times we don't state it explicitly, but they're all kind of inherent. But it's important for us to remember that, because you could have situations like this where those play a huge role in terms of how the overall structure behaves.
So if we have any eccentricity or any material defects or distributions that are not isotropic, then we would have the deflection occurring even if it was uniaxial. I think. Oh, and then next up we have this equation that I included from my MSc or materials class, where we talk about how we can actually quantify basically crack propagation, where we have K1C specifically as a material property, specific to the material, and this is occurring mainly under the condition that it's under tension. That's the basic assumption that we're making here. And the equation you'll see includes the stress, where we're having it in tension, times the square root of pi times c, where c is the length of the current crack. And using this, you can predict future behaviors.
So now I'm going to talk about hydrostatic forces, which are caused by incompressible fluids. So we can relate hydrostatic forces to stress, and stress being pressure, by the equation of force equals pressure times area. Also, as an example of a submarine, we can use hoop stress equations, since submarine is a thin-walled structure, also mainly a monocoque thin-walled structure. We can relate the difference in pressures on outside and inside times the radius of the structure divided by thickness of the structure to get the stress, and which is also being the pressure in a way, this scenario. And also same for longitudinal stress, it is a similar equation. Then we can relate stress to strain using the bulk modulus equation. We can rearrange it to make the difference in pressures is equal to negative K times the volumetric strain. Then, since it's a volumetric strain, it is a change in volume divided by initial volume. It can be, if it's negative, it will mean compression. If it's positive, it will mean expansion. And hence, deformation, it's a general uniform shrinking or expansion.
So whenever we say pressure, we automatically mean negative stress, negative normal stress. And the volumetric change is also negative because it's a reduction in volume. So if you're writing stress versus the volumetric strain, then you don't need the negative sign. But if you're writing it to pressure versus that, because pressure is assumed positive when it is compressive, right? So then you do need the negative sign.
I guess like if it's a difference in pressures, if for example on the inside you have a high pressure.
True. Yeah, it could be external pressure. As in the case of the submarine, that's probably much more relevant. Yeah, true. It's the difference that matters, the external internal pressure difference. And that's applicable not just submarines, even in the aircraft, passenger aircraft which fly beyond a certain altitude when you have internal pressurization and the outside atmospheric pressure at that altitude.
Okay, this is spring and damper system. So this is system dynamics, mainly from system dynamics, and then also a little physics 1 with Hooke's law. Damping force is Fd with the derivative of y times the damping coefficient, and then here we have k, and then usually we have x, right? But in this case it's y because of the example there. And that is spring constant, so the damping coefficient is ns over m, while the spring constant is n over m for units. And then, how do we take these forces and relate that into an equilibrium equation so we can have a spring mass damper kind of system here where an equilibrium equation kind of dictates how this system behaves, right? We have the damper, we have the spring, and then the mass acting in one direction, and then we have gravity here on this other side. So it just shows how the system behaves. Keep going. And this occurs due to the deformation of the spring, so the change in length due to compression, right? So that is, in essence, what we're talking about here. Yeah.
So now we go to torque.
Should we not know? Wait, just,
Yeah, go ahead.
I'm not, can I say?
Yeah, please.
Should we not know the fact that damping is a variant of velocity? He missed it out. So when you say damping force there,
Yeah.
it's a velocity derivative.
Right. It's just a derivative of the y, right? So I just wanted to.
That's the fundamental.
Right.
You're saying c is a function of the velocity.
Whatever.
Huh?
Damping force, damping coefficient is
Yeah.
a function of
So
velocity.
damping coefficient would be like a constant based on like whatever system you're looking at, versus dy dt would just be like derivative of position, then would be the velocity.
Yeah, it's just
Unless
derivative
I
of
think about
position.
velocity, because you can't produce them.
Yeah, so that's what they have already as dy by dt
dy
is
by
the velocity.
Yeah,
So you see, this is the velocity.
Yeah,
Right.
I feel he missed it out.
Okay, it's there.
Oh,
He's a youngster, I thought.
Right.
No. I understood that. I just wanted to. I just want to keep everything position based, right? It's just a change.
So now torque, which is movement due to moment, we can relate torque to stress using the following equation, which is specific for a rod, and it varies a lot based on the geometry of the object, which we're going to talk slightly about later. So T being the torque, R being the radius of the rod, and J being the torsional constant. And hence, using the formula for the shear modulus, we can relate the shear stress to shear strain. Then going further, we can then relate shear strain to torsion applied in a shaft. So for this specific example, torsional strain will be tan of phi being the angle by which basically the material shifted. And here some examples of torsional coefficients for thin-walled cross-sections with uniform cross-sectional sides. First one being relevant for closed thin-walled cross-sections, and the second one being for open cross-sections. Basically, you sum up the length of the cross-section and then multiply it by thickness to basically get the cross-sectional area of the object.
Yeah, I'm glad you brought this up because this is one of the important things in structural analysis, especially related to flight vehicle structures, because you'll have both closed and open sections. So there's a huge difference in how the J is defined for either of them, and that makes a difference in terms of the overall torsional behavior of those shafts. So where torques are large, you will prefer to use close cross sections, because that J first expression that you have will give you a much larger torsional stiffness, GJ, whereas this will give you much smaller torsional stiffness, where you want it to be very flexible in torsion. You typically go for this, or if the torque is not the dominant load, you have other loads which are more dominant, then you still go for an open kind of a cross section.
And also earlier, Matt mentioned about the other torsional coefficients, also based on geometry, like there was for beams, for specific holes in an object. So yeah, that's like as an extra values of J that also depend on geometry. And yeah, that is, at the end, we have the final equation that basically relates the deformation all the way back to loads. As we can see, it uses torque in the equation to find the angle by which the object is.
Just start there. It's fine. Here? No. Go. Yeah. Yeah. So okay, I think the best way to introduce this topic is to start with deformation, because in essence it is a deformation-based problem, right? So I start with a statement. Deformation occurs differently theoretically versus experimentally, right? Now let's see what that means in a graphic sense. Yeah. Okay. Now we can see that theoretically, with the true stress and strain curve here, it just keeps going, right? Obviously, necking occurs at different points here because of that. And then, when we're looking at graphs, we're usually looking at the engineering or, the experimental version of what's going on, because that's more useful to us. But equation, like based on like equations and based on theory, it would be a completely different curve, and the curve would change, like end at a different location, have a different relationship. Here it shows more of a linear relationship, right? So so true versus engineering strain, that means that a true strain would have a different relationship. So using this integral here, we can see that there is a direct relationship here, but it is definitely modified, right? So here we can relate stress and strain for the true variables, right? So whether that's plotting it logarithmically, for the true stress and the true strain, and we can see here that the elastic modulus is used to relate the two. And then here we can also see that bulk modulus can be used if we use strain hardening exponent, which is just a separate term, right? And then so it's just relating true stress to normal stress, right? And that's another relationship as well. Okay.
And so going back to beams again, we wanted to include these kind of like generic statics problems of beam loading and beam moments for kind of the core forces, also kind of extending that to the equilibrium equations. And so like the three like generic beam types you see, you have like the fixed, so whether it's attached to a wall, it's usually kind of how you illustrate it, or any other way that could be fixed. The roller, and then the pin or hinge. And so of course these are all going to act differently and have different forces and moments. And so with the fixed, of course, being totally fixed, you have the forces in all the directions, so it's not it's balanced in terms of like movement. It's also balanced in terms of rotation due to this moment, versus when you have the roller bearing, of course, it's fixed in the vertically, but it can still roll side to side. It can still have the rotation. With a pin and a hinged, it's kind of a mix between the two, where you have it fixed in terms of location, but of course it can still rotate, sort of like a diving board would. And so of course these all have different applications in terms of what you're trying to go for. So we see these kind of throughout some day-to-day life. So we're using something like a bridge. It's going to be very fixed. I said that something like a diving board is kind of a good example of something that's that pinned, versus a roller could be anytime, you know, you're trying to, sometimes you say it in a very simple way. If you're trying to move something, you can move it just by rolling it across. If it's heavy, it's rolling it across a roller. It's kind of like a rudimentary way to move something without like more complicated machinery. And so when we talk about extendedness of the equilibrium equations that we would use in statics, that kind of best relate to this fixed example. Why is it doing that? Oh my gosh. I don't know what's happening. Okay, whatever. So we talk about in statics, then when we talk about something is static, it means we have these equilibrium equations. So you have the sum of forces in all directions, of course, is equal to 0, as well as the sum of moments in all directions is equal to 0. So of course, if all these equilibrium equations don't hold true, then something isn't static. And so that's, where, of course, something that's, dynamic comes in. And we're talking about dynamics problems where maybe some or all of these are 0, but not the rest of them. And so, maybe, like, for example, if you start to have something that it's pinned, but you don't necessarily have the sum of moments equal to 0, then that's to start to cause rotation, then it's not really a statics problem. I think that's everything there.
So when we talk about loading conditions, another load that occurs is temperature change, because materials have thermal expansion coefficients that basically determine how much they will expand under a temperature change. This can become an issue in engineering or in structures in general if you do have a temperature change, or if you have a difference in the coefficient where you can cause two metals to either contract or be in tension based on the relation between their coefficients.
So this is kind of related to what we'd actually just talked about in one of our previous homeworks, where we talked about the compatibility of composites. And so one of the points we made was, like, if you're looking at like aluminum matrix composites, that you had to have that compatibility because of thermal expansion, where you could have delamination of the layers because of this expansion that can occur due to high heating that you might see within some of those composites.
We're zoomed in a little. Okay. So you can see that the strain, or the thermal strain, is caused by this is given by the equation where alpha, the thermal expansion coefficient, multiplied by the change in temperature will give us this strain caused by this change in temperature. And we have a specific example where we put in a constitutive law to show how this strain can exactly result in a stress caused by these constraints that are put on the structure. And so in this example, you'll see that the structure here is free to expand in the y direction and the vertical direction. That's why you'll see that there's no stress applied in the y direction. While it's constrained in the x direction, that's why you see there is a stress in the x direction. You'll notice that while we do have a stress in the x direction, there's also no strain because there's no change in length. And we can actually derive this. You can use this to derive the strains in the other directions based on what we know. So we know for strain in the y direction, we know that basically the mechanical strain we have here, there's going to be no stress, and so the remainder of the equation will give us whatever the strain will be in the y. And using this, we can also derive what the stress in the x will be based on whatever constraints we have. You'll notice that the answer here is negative because when we're expanding outwards, the reacting forces are pressing in on us. So it's going to be a compressive stress that's being applied.
So we can talk about strain energy right now. We'll start with a very basic physics 1 concept and kind of go to a concept that's used much later, in later classes. It's something that this topic can really show us that whole path, right? So we'll start with work. Work is just basically force times displacement. We also know by the work energy theorem that work is the change in energy, right? So that's that direct pipeline. So conservation of energy, right now I'm talking about potential energy and kinetic energy, but later, obviously, this all applies to strain energy as well. So conservation of energy before...
So strain energy is an example of the potential energy. It's one of the kinds of many different kinds of potential energy.
Right, yeah. So, this is just general. I just wanted to start general. So conservation of energy, the energy that occurs before has to be after. So this is just like conservation of mass, conservation of energy. In essence, an equilibrium equation, right? So, all right, so let's talk about the strain energy equations. Here we can see that strain energy is equal to 1/2 times the volume of an object times the stress and the strain. So this would be, an example of how strain energy relates to both stress and strain. We'll also see here that strain energy is also directly related to a force and a change in length. So that would be like a load as well. Right?
Yeah. So these are valid if you're talking of the V as an infinitesimal element, not the volume of the entire object.
Right.
Because in the object, remember, stress and strain are functions of the spatial location.
Right.
Apart from time.
Right.
So it will vary from one point to another within the object. So you can't just multiply the volume with the stress and the strain. Okay.
Yeah.
So even if you average out the stress and the strain, it will not work. You'll have to actually do the integration of sigma epsilon dV.
Okay.
Same thing with f dx or f
Right, so
delta, f d
Yeah,
delta.
so it's specifically used, not like just a general equation. Yeah. Okay. What happened to my thing on this side? Oh, there it is. Okay. So the modules of resistance. So we talked about the stress strain curve a while back, and the modulus of resilience is the area underneath the linear portion, so that initial linear portion of the stress strain curve. Now, what does resilience mean? Resilience is the ability for a material to absorb energy when load is applied, or to release energy when it's unloaded, right? And then the definition of strain energy is when energy is stored by a system undergoing deformation, right?
Okay.
So,
So this is under the assumption that the proportionality limit and the yield point are the same.
Okay.
Need not be. So in terms of the linear limit and the elastic limit, they can be in some materials, they could be different from each other. So all the way up to elastic limit, even though part of the curve is non-linear,
Right.
you will still be able to get back, and you have the resilience
Okay.
over there.
Okay. I think in my research, I just used this. Yeah, I understand what you're saying. Okay. It's just.
I think he had one
so I
more
guess
figure below.
Fiber diameter defects.
That's different.
So this is something we covered extensively in class. Is that as the fiber diameter increases, the tensile strength tends to decrease. Now that's not because of a specific property. It's more because of manufacturing defects, right? So when we're talking about cracks that occur, so this is again an example of experimental versus theoretical, right?
Mm-hmm.
So theoretical, the relationship would be completely different, but in an experimental sense, when we create these fibers, when there's during the manufacturing process, crack propagation increases because there's more space for that to occur. Right?
So while manufacturing is the main reason that you would have the defects, it's also, even if you're manufactured with relatively very low level of defect density, the handling process can always induce, because these are very flimsy.
Yeah.
So how you actually protect, how you transport, all these things will matter in terms of the defect density when you actually utilize it in a structure, in a composite and first, and then in a structure.
And so the last part, we covered this yesterday, but we're going to go over it again.